Okay, so our third contestant is Christopher Miller. He's from the Physical Life Sciences Directorate. And the title of his slam is From Micro Scale to Macro Scale, Designing Better Explosives.
I hope we have some bakers listening in because we're about to dive into a delicious cake metaphor. You have some eggs, flour, butter, sugar, you mix it all up, throw it in an oven, boom, you have a cake. Say you change one of those things. Maybe you take out the rising agent and you no longer really have a cake, do you? Instead, you have something closer to, say, a brownie. How do you know? Are you going to end up with a brownie? Are you going to end up with cake? Well, we've all cooked before. We know there's a cookbook for these things. Somebody has done this before us, and more importantly, has written down what works and what doesn't. It's an old metaphor, but surprisingly applicable to designing new explosives. There are ingredients, there are formulation processes. You change either one of those at all, you're going to end up with a new kind of explosive. So the question becomes, how does changing your ingredients change your output, especially when you need to have a very particular explosive for a very particular purpose? Well, an idea was put forth to incorporate something called microballoons. And these are exactly what they sound like. They're little hollow glass beads. You miniaturize, shrink them down, mix them into your formulation there. The idea being that this is a way to artificially control the porosity, but we're changing the input. So how does that change the output? So I am a modeler, for better or worse, so I set up a number of simulations here. This, what we have, is an explosive being impacted by something, and I varied two things here. One, I looked at the number of microballoons, and two, I looked at the size of each of these microballoons. These are pretty complicated simulations that years ago this would not have been possible to solve. Thanks to the power of Livermore's own high-performance computing, we can shove as much physics in there as we can reasonably imagine and simply let it play out. Now, whereas an experiment may take weeks, even months to set up, I can run thousands of these overnight. But what did I learn? Well, if you have small microballoons, you end up with small amounts of reaction. Larger microballoons, you end up with larger amounts of reaction. Even larger microballoons, back down to small amounts of reaction. Yeah, it threw me for a loop too. Turns out there's a hidden optimization going on under the hood we didn't really know anything about. If you start making these things too big, it ends up being inefficient to collapse them. Of course, this is just one variable looked at. You could look at other things. You could try changing the microballoon material. You could try changing the balloon wall thickness. You know what? You could even try changing the balloon shape here. Every one of these is important to study because every single one of these is a new page in your explosives cookbook. Because at the end of the day, when it comes down to it, we'd really prefer this to be more of a science than an art. Thank you.